So I'm Sam Smith. I'm a research scientist at DeepMind. And so today I'm presenting a work that I'm really excited about on the origin of implicit regularization in stochastic gradient descent. So if people have questions during the talk, then feel free to just shout out and I'll do my best to answer. That's totally fine by me. So of course, I'm not going to be presenting just my own work. So this is the result of a collaboration between myself, Sohamdi, David Barrett, and Benoit Durand. So Soham and David are both at DeepMind with me, and then Benoit works at Google. And I'll be presenting two recent papers. So both of these are actually at ICLR 2021 this year. The paper at the top was actually, I wasn't involved in at all, so that's a paper from David and Benoit. And then when Soham and I saw that work, we got really excited about it, and then we started a collaboration built on that. So let's just sort of set the scene. So SGD, of course, is remarkably simple, and yet it remains surprisingly popular in deep learning, especially for computer vision. And so today we're going to be considering the simplest possible version of SGD, where we just take updates proportional to a learning rate epsilon, and then an estimate of the gradient on a batch of B examples, where B is typically much smaller than n, the size of the training set. So even at this very early point in the talk, we have an important decision to make, which is how we're going to sample these mini batches from the data set. And so there are kind of two popular schemes in the literature. The first is random sampling, where we just randomly draw B examples from the entire data set at every step. And then the second scheme is random shuffling, where we sort of assume that the data set is ordered, and we iterate through the data set from start to finish, and then we have the option of shuffling the data set between epochs. And so one point I'd like to make right at the start of the talk is that random sampling is often actually quite impractical, especially for large data sets. So many of the data sets that we'd like to train on are so large that we don't store them in one place. So the data set is partitioned into multiple subsets on different devices. And so it clearly wouldn't be very convenient to be randomly drawing examples from the entire data set at every step. And so practitioners almost always use random shuffling in practice in deep learning. And yet most theoretical work tends to focus on random sampling. And so one of the kind of key themes of today is going to be exploring the question of whether random shuffling might be different to random sampling. And so the key kind of mystery that we'd like to be able to understand is, why does SGD generalize better when we use finite learning rates? So this is not a novel observation. So this has been seen by many previous authors. But I'm just showing you a simple example of this phenomenon in this figure on the left. So I'm training a wide ResNet on CFAR10 with a constant learning rate. And the orange curve shows you the accuracy achieved on the training set for a range of learning rates. And then the blue curve shows you the accuracy achieved on the test set for the same range of learning rates. And so one thing that you'll probably immediately notice is the learning rate which maximizes the test accuracy is much larger than the learning rate which maximizes the training accuracy. And in fact, the learning rate that is best on the training set is so large that it actually impedes convergence on the training set. So this has been kind of like a key mystery that people have wanted to understand in the theory of deep learning, which we're going to attack today. And the kind of informal version of the claim I'm going to make in the talk today is that the iterates of SGD, even when the learning rate is finite, stay close to the path of a gradient flow. But rather than staying close to the path of gradient flow on the training loss, they stay close to the path of gradient flow on a modified loss. And this modified loss has the form shown here, where it's composed of the training loss C of omega, and then a source of implicit regularization R of omega. And the scale of this implicit regularization is proportional to the learning rate. And so then this kind of immediately explains this figure on the left, because we can sort of simply observe that as we increase the learning rate, we're implicitly achieving stronger regularization. And as a result, we achieve better test performance at the expense of worse performance on the training set, just like we would for explicit regularization. And so later in the talk, I'm going to derive for you the specific form of this implicit regularization, but I just wanted to kind of sort of preempt the key result at the start. Okay, so in order to try and explain like the role of finite learning rates in training, I'm going to exploit a connection between optimization and numerical integration. Of course, in deep learning, we're often interested in the path taken by gradient descent, or SGD, where we take finite steps on a gradient of the loss. But we all know that in the limit of vanishing learning rates, the path of gradient descent will coincide with the path of gradient flow. And gradient flow is just a first order ODE. And so if we are in the numerical integration community, then we'd say, well, there are many first order ODEs that we'd like to be able to solve, but we typically can't solve ODEs exactly, and so we're forced to approximate them with systems of discrete steps. And so the Euler update, which corresponds to gradient descent, is just one system of discrete steps for approximating a first order ODE. And so the reason that this connection is convenient is that there are many tools in this community for understanding the approximation error that arises when you replace a continuous ODE by a system of discrete steps. And so we're just going to borrow their tools to try and understand the role of finite learning rates in optimization. Okay, so that's kind of like the high level pitch. And the particular tool that we're going to use today is backward error analysis. And so as I just said, the sort of setting is that we imagine we want to solve some continuous ODE f of omega, but we're forced to approximate it with discrete updates. And the consequence of that is that every discrete update will step slightly off of the path of the underlying flow, as I show in this kind of simple diagram in the top right. And so over a series of updates, a bias is going to emerge between the discrete iterates and the solution to the continuous ODE. And we'd like to be able to capture that bias. And so the sort of trick of backward error analysis is that we're going to introduce ancillary modified flow. And so that's this flow here, f tilde. And so this modified flow has got two key properties. So the first property is that it's just a Taylor expansion in powers of the step size epsilon, with a series of correction terms, f1, f2, and so on. And then the second property of this modified flow is that the zeroth order term in this Taylor expansion is just the original vector field f. So in the limit that the learning rate goes to 0, the modified flow would just coincide with the ODE. And then for finite step sizes, the modified flow is going to differ from the original continuous ODE. And so now our goal is we'd like to be able to derive correction terms f1, f2, f3, and so on, which ensure that the discrete updates on the original flow, shown in red in this diagram, will coincide with the continuous solution to this modified flow, shown in purple. And the claim is that we should be able to identify a modified flow with this property so long as the learning rate is not too large. So that's kind of the idea of backward error analysis. And I think at first, at least to me, it seems like implausible that such a flow would exist. So I'm going to start the talk by just deriving in a couple slides the first order correction term in this expansion. So that's going to be our goal in the next couple of minutes, is just to derive the first correction term f1 for this modified flow. So I'm actually not going to use kind of like the classic derivation, but instead use a kind of optimization inspired version of the proof, which I think is kind of more intuitive to people coming from the deep learning community. And so the idea of this proof is as follows. So I'm first going to imagine the consequences of taking n Euler steps on this modified vector field f tilde with some step size alpha. And then I'm going to Taylor expand the value of the nth iterate after taking n steps. And then in the second step, I'm going to send n to infinity and simultaneously set this kind of imagined step size alpha to epsilon over n. And so of course we know that in the limit of vanishing step sizes alpha, then the iterates of the discrete updates would just coincide with the underlying flow. So this second step just ensures that this nth iterate actually lies exactly on the solution to the modified flow. And once we know the value of the solution to the modified flow, we can just equate that solution to a discrete update on the original flow. And so long as the discrete update coincides with the solution to the modified flow, then we've kind of satisfied our goal. So that sounds a little bit intense, but I promise you it won't seem that hard when we go through it. So to start off, we're going to just apply n Euler updates on this modified flow and then Taylor expand. So of course, omega t plus n is just omega t plus alpha f tilde omega t, and then we do alpha f tilde at omega t plus 1, alpha f tilde omega t plus 2, and so on. And now in the second step, I'm just going to remember that I implicitly know all of these iterates. So for example, omega t plus 1 is just omega t plus alpha f tilde omega t. And similarly for omega t plus 2, I'd have a slightly longer expression. So I kind of obtain this sort of intimidating looking implicit equation for the value of the nth iterate. But of course I get lucky because I only need to Taylor expand this result. So if I now just take this sort of nightmarish implicit equation, and then I do a Taylor expansion up to second order in alpha, well, at first order in alpha, I'm just going to collect n terms of type f tilde omega t, as you would expect. And then when I Taylor expand to second order in alpha, I'm going to collect terms of type grad f tilde f tilde. And it's not immediately intuitive, but if you trust me, if you just count the number of terms of this type, there are n over 2, n minus 1 terms of this type. And then I'm just going to collect everything at higher order in alpha. So that's kind of the first step. And now in the second step, we're going to send the number of updates n to infinity and simultaneously set this step size alpha to epsilon over n. So of course, the reason I'm doing that is that we know that in the limit of vanishing step size alpha, omega t plus n will just coincide exactly with the solution to the modified flow omega t plus epsilon. And so that will just have the form written here. And so we're really almost there. So now I'm just going to remember, the sort of the expression for the modified flow f tilde. So remember, f tilde is just this Taylor expansion of correction terms f1, f2, and so on. So I just substitute that in, and then I just regroup the terms to arrive at this kind of final result here. So now we just notice that the first two terms in this Taylor expansion of the solution to the modified flow is just exactly the Euler step. So up to first order in epsilon, a single discrete update on the original vector field f would coincide with the solution to the modified flow. But of course, the Euler step doesn't have any updates at epsilon squared. And so if I want to ensure that my modified flow lies on the same location as the discrete iterates, then all I've got to do is make sure that these higher order contributions vanish. And so if I just rearrange to ensure that this higher order contribution vanishes, then I immediately obtain the first order correction to the modified flow. And similarly, if I had Taylor expanded to order epsilon cubed, I would have identified f2, and to 4 I would get f3, and so on. So, it's actually surprisingly straightforward. So, given that result, let's just quickly obtain the modified flow for gradient descent. So, we're imagining doing, gradient descent on the full batch loss, and we want to identify an ODE of type omega dot is f tilde omega, where f tilde has this form, which will coincide with those discrete iterates. So all I have to do is just, remember that for gradient descent, the original vector field f would be minus the full batch gradient. And then if I substitute that into the expression I derived for the first order correction, the first order correction will just be a half times the Hessian vector product of the Hessian and the gradient. And I can simplify that slightly by just remembering that this Hessian vector product is just equal to the gradient of the squared Euclidean norm of the gradient. So just like grouping that all together, we've just proved that so long as the learning rate is not too large, then the discrete iterates of gradient descent would actually coincide with the solution to an ODE. And remarkably, that ODE is still gradient flow. but not gradient flow on the training loss C of omega, but rather gradient flow on this modified loss C tilde. And as we saw right at the start of the talk, this modified loss C tilde will contain this source of implicit regularization on the right. And the scale of this implicit regularizer on the right is proportional to the learning rate. So, I think this is like a really kind of neat result. It's like very simple to derive, but quite surprising, I think. So like I claim like no credit for this. So like, this result was introduced by David and Benoit in their recent paper. And just to convince you empirically that this is a reasonable claim. So in this kind of quick sketch at the top right, I'm showing you the dynamics when I train on just like a simple poorly conditioned like 2D quadratic. And so training is just like starting in the top right corner and progressing towards the optimum at the bottom. And so the blue line shows you the path of gradient flow, or the path of very small learning rate Euler updates. And then this orange line shows you the path taken by kind of finite learning rate discrete steps. And then finally, the dotted green line shows you the path predicted by this modified flow. So, for learning rates that are finite but not too large, it really is the case that the discrete iterates stay close to this modified ODE. And I've also kind of included some like large learning rates in red and purple just to kind of emphasize that, this is like a Taylor expansion, so it holds when the learning rate is finite but not too large. So like once the learning rate is chaotic, this would all break down. But for kind of non-chaotic finite learning rates, this is a pretty good description. I also just wanted to highlight that in a slightly earlier work, Lee et al. Provided like an extension of backward error analysis to random sampling SGD. So this is like a really beautiful paper that I also encourage people to check out. So before I move on to the case of SGD, which is like the main purpose of this talk, I just thought I'd try to give you guys some intuition for why this modified loss would appear. And so the intuition is actually really simple. So one way you could think about gradient descent is that if we think of gradient descent as trying to solve an underlying ODE, then on average, the gradient is always half a step stale, because we always evaluate the gradient at the start of the update, and then we progress by time epsilon. So you could think of the gradient as being on average stale by a time of epsilon over 2. And so one way we could like model that is you could imagine like kind of like an inner loop procedure where you start at the parameters omega, you evaluate the gradient, and you take a step with sort of size epsilon over 2, but in the positive direction. So you sort of step backwards, like up the loss surface. And then you reevaluate the gradient at this kind of stale location. And that would be kind of like similar to this kind of implicit effect from gradient descent. And if we just like very straightforwardly Taylor expand this loss, we immediately obtain the same result. So I think this is kind of probably the best way to think about this effect is like, because gradient descent evaluates the gradient at the start of the update, it's effectively stale, and there's an associated regularizer with the fact that the gradient is stale. And just as like a quick aside, so there was this recent paper, sharpness-aware minimization, which it doesn't like exactly correspond with this analogy, but they essentially propose like a training inner loop of exactly this type, where you start at the parameters, you take a step in the positive direction of the gradient before reevaluating the gradient, and found that it's actually very effective as a regularizer in deep learning. So that's kind of just like a nice connection. Okay, so that was like the gradient descent part of the talk. Are there any questions before I move on to SGD?
So the regularizer is of the form the gradient of the objective and not the gradient of the parameters or anything like that.
Yeah, so it's the gradient of the loss evaluated at the current parameters, and then you square that.
Thank you.
Maybe this is a stupid question, but do you have any intuition why that particular regularizer might improve test performance?
Yeah, so that's not a stupid question. That's actually not a stupid question at all. I'm going to give an answer which seems very bizarre halfway through the talk. I actually don't think that this term enhances generalization very much. And so basically when we do the extension to SGD, we're going to like get an additional term here on the right. And I think it's that like additional term that arises from SGD that like makes this effective. And then like the reason I think that this sharpness aware minimization method works is because they do it with mini batch gradients. And I think if they did it with full batch gradients, it wouldn't work. That's like my suspicion.
Okay, thanks.
Okay, cool. So I'll move on to the second half. Okay, so we're now going to try and extend this analysis to random shuffling SGD. So just to kind of very quickly define random shuffling SGD. So we're now going to be considering an algorithm where we take updates proportional to a learning rate and then a gradient estimated on a batch of B examples. But rather than that gradient just being a random sample from the data set, every mini batch C hat I is going to be indexing a specific set of B examples from the data set, like a specific fixed set of examples. So I've introduced this kind of integer m, where m is just like n over b, i.e. it's just a number of updates in one epoch of training, just for convenience. Okay, so what's kind of the key property, right, that we're going to exploit with random shuffling SGD? So the key property is just that, you know, the full batch loss, which is just the average over all of the training examples of the per example losses, is simultaneously exactly equal to the average over all the mini batches of the mini batch losses. So this property that like every example appears in one and only one mini batch is going to be kind of like the key property for random shuffling SGD. Okay, so this like derivation is a little bit more complicated, or they're not that complicated. So I'm just gonna like go through the claim at the start. So the claim I'm gonna make is that if you run one epoch of random shuffling SGD, and then you ask, you know, what is the mean value of the iterate at the end of the epoch, averaged over like all sequences of mini batches that you could have seen, then that expected iterate lies on the solution to a continuous ODE, so long as the learning rate is not too large. And remarkably, just as we saw for gradient descent, this ODE is still a gradient flow. And again, just as we saw for gradient descent, it's not gradient flow on the training loss, but gradient flow on a modified loss. And this modified loss contains this source of implicit regularization on the right. And so just as before, this implicit regularization is proportional to the learning rate. So the larger we make the learning rate, the more strongly SGD is regularized. And then kind of the nature of the regularizer is it's just going to take an average over the mini batch gradients of these squared Euclidean norms. So that's kind of going to be the key claim, which at least to me is pretty surprising. So just to kind of clarify one kind of slightly strange aspect of how we did the proof. So in order to do the proof, we're actually going to assume that the composition of the mini batches is fixed. And so when I take this expectation, I'm averaging over the order in which those mini batches could have arrived, but I'm not averaging over the composition of the mini batches. So that would like explain why I have like specific mini batches C hat K appearing here in the modified loss. So of course, this is like exactly equivalent to random shuffling SGD when the batch size is 1, and then it's like slightly different when the batch size is larger than 1. So it's just like a small technicality. Okay, so to derive this result, we're gonna like do something which just like looks outrageous. So just like before, we're gonna imagine the consequence of taking many steps. But this time, we're going to imagine the consequences of an entire epoch of training and then Taylor expand that entire epoch. So the mth iterate at the end of one epoch would just be the initial parameter minus the learning rate times the gradient at the 0th parameter evaluated on the 0th batch, the gradient at the first parameter evaluated on the first batch, second at the second, and so on. So just like before, we can just like implicitly substitute all of the solutions for omega 1, omega 2, omega 3, and so on. And again, just as before, we can now just Taylor expand this expression. So it's going to be a little bit more complicated now because we're going to have to remember which mini batch we evaluate a term at. So to first order in epsilon, we're just going to collect a term of type grad C hat for every mini batch J that appeared in the epoch. But then at order epsilon squared, we're going to get this kind of double sum over the like Hessian vector product. So you'll notice this is like kind of the same as before. It's just a Hessian vector product in the mini-batch gradients, but now we have to remember which particular mini-batch we evaluate a term at. But there's like immediately something like, I mean, it's kind of obvious, but also like kind of quite surprising here, which is that, you know, because this sum runs over all of the mini-batches, then in this kind of first order term in epsilon, we just obtain the full batch gradient grad C. So unlike random sampling SGD, for random shuffling SGD, there's like no variance in the iterates up to first order in the learning rate. So like in the limit of kind of like vanishing learning rates, random shuffling SGD just follows the exact same path as gradient descent. So that's the first thing that's maybe surprising. And then at second order in epsilon, we have this like term chi, which just captures this double sum. So this term chi is a random variable, and it's a random variable because it cares about the order in which the mini batches arrived through this k less than j term here. But it's not like a mean zero random variable, so it's like a random variable containing both bias and variance. And so like for simplicity, we're just going to try and evaluate the mean value, the bias of this term. So, you know, this is just where we were before. So we decided that the mth iterate is just the initial iterate minus a term in the full batch gradient, and then this term in chi. Chi has this form. So we'd like to evaluate the mean value of chi. And so the trick we're going to play is that like chi depends on the orders of the mini batches through this sum over mini batches k less than j. So if we now just imagine averaging over all possible sequences of mini batches, then like for every sequence 1, 2, 3, you always get the reverse sequence 3, 2, 1. And so, you know, as a result, this like sum over k less than j is going to convert into a half times the sum over k not equal to j. And so we're going to like remove this dependence on the order. So that's like the key trick. And then having done that, we can just remember that like if this was like a full sum over all values of k, then this term here would just reduce down to the Hessian vector product of the full batch gradients. And now I just have to subtract off the missing diagonal. And the missing diagonal just gives me a term in the Hessian vector products of the mini batch gradients. And I can just simplify that further just as before. So that's like kind of the key part. And so essentially what we've just done is we proved that so long as the learning rate is not too big, then the expected value of the mth iterate at the end of one epoch, you know, just lies at exactly this location here. And now we're just going to remember that, okay, like earlier in the talk, we derived the solution to this modified ODE f tilde. So just like copying down the result we derived earlier, we know that the solution to this like modified ODE has exactly this form with this correction term f1. So all we have to do is just equate the mean value of the iterate at the end of the epoch to the solution to the ODE, and then solve for S1, and then we're done. As when we do that, we arrive at exactly the result I claimed. So that's like the whole proof. So we've just shown that the mean value of the iterate at the end of one epoch coincides with the solution to an ODE, so long as the learning rate is not too big. That ODE is a gradient flow, but it's not gradient flow on the training loss, it's gradient flow on this modified loss containing this implicit regularizer. So like, yeah, I think that's like pretty surprising. So of course, like we made some like pretty strong assumptions. And so the key strong assumption that we made is we've assumed that terms of order m cubed, epsilon cubed are small, where m is the number of mini batches in one epoch of training. So like this is clearly quite a strong assumption, because if the data set is big, then like m epsilon is presumably large, and so you might expect these terms to be large as well. So we have like quite a long discussion in the paper of situations where you might reasonably expect these corrections at higher order to be small and situations where you'd expect them to be large. But just to kind of argue today that like this is still like a valuable analysis, one sort of observation to make is that this is like a strictly less strong assumption than gradient flow, because gradient flow doesn't only neglect terms at epsilon cubed, but it even neglects terms at epsilon squared. And I think we'd all be quite comfortable saying that gradient flow gives us some useful intuition about the behavior of gradient descent in SGD. And so like on that basis, it's sort of reasonable to assume that there's like some reasonable intuition contained here as well. The second thing that I think is quite surprising about this analysis is that normally when we study SGD, we focus on the variance in the iterates, whereas this analysis is focused entirely on the bias. So like at first sight, that's quite surprising, and we would like definitely love to be able to capture the variance as well. But the reason we made this choice is precisely because when you study random shuffling as opposed to random sampling, then like the variance of the Taylor expansion for small learning rates is actually heavily suppressed by the fact that you're using random shuffling. And so we therefore kind of suspected that bias is actually more important than people think. So that's kind of the inspiration for that step. Okay, so the final little piece of theory. Yeah, sorry, go ahead.
Sam, there was a comment in the chat box. Pascale, would you like to read out your comment? Pascale around? So the comment read, it seems connected to the regularization term you find in contractive autoencoders. Does that make any sense that you can comment on?
I guess I'm not an autoencoder expert, so I couldn't say, but it could be. I should say I can't see the chat box. So if anybody has a question, then do just shout at me, because otherwise I won't.
Sorry, I was brewing some coffee. Yeah, basically in this architecture, you have this regularization term where you, like in order to find some parameters, like an encoder that whose results don't change much, if you do small perturbations to the input, they basically use the Jacobian of the encoder as the norm of the Jacobian of the encoder as a regularization term to find kind of smooth functions. And this seems very related to that in some sense. I'm wondering whether there's some connection between the two. And this maybe can also maybe be used as an explanation on why SGD and gradient descent work in practice. Like I was just wondering whether this makes sense.
Yeah, that makes total sense. So yeah, like I agree. There are definitely are explicit regularizers that are kind of, or at least somewhat similar in form to this. So yeah, I think I entirely agree with that.
Thanks.
Okay, so like the final piece of theory we'd like to do is like one like unfortunate aspect of the way that we did this analysis is that this modified loss depends on the like specific mini batches that we sample in one epoch, like as a consequence of the fact that we like held the composition fixed. And so it's not immediately clear, okay, like how does the strength of this regularizer depend on the batch size, which is like a question people often want to know. And so in order to answer that question, we're now just going to imagine randomly shuffling the data set and then redrawing these mini batches C hat I, and basically asking, okay, like what's the expected value of this modified loss for a random set of mini batches drawn from that data set? So when you do that, things become very simple because you just get the training loss, and then this term on the right just reduces to the expected value of the squared Euclidean norm of like a single mini batch drawn at random from the whole data set. And although I'm not going to show it here, you can evaluate that expectation. And so what you find is that the kind of modified loss for SGD actually separates out very straightforwardly into three components. So the first component is just the original training loss. This second component is precisely the implicit regularizer we derived for full batch gradient descent. So that term is still present for SGD. And if you only had these two terms, then SGD would just follow the same dynamics as gradient descent. But finally, in addition, we have this term on the right. And this term on the right is going to capture like all of the contributions from mini batching in terms of the dynamics. And so the first really nice property of this final term is that it's just proportional to the trace of the per example covariance matrix. So like intuitively, what that means is that SGD is like implicitly penalized from regions of parameter space where the gradients of different examples disagree, and it's like implicitly attracted to regions of parameter space where the gradients of different examples agree. So that's kind of like how we interpret this like regularization effect. And then the second thing that's like nice to notice about this term is that the scale of this implicit regularizer arising from mini batching is proportional to the ratio of the learning rate to the batch size. So this is like consistent with this kind of common empirical observation that when we double the batch size, the optimal learning rate typically also doubles. So that's like kind of consistent with this this analysis. So that's nice. So yeah, okay. So that's like the end of the theory. So now I just thought I'd show you a few experiments to try and convince you that this is like a reasonable analysis. So what we're going to do is we're just going to define an explicitly regularized loss C mod, where we just take the modified loss associated with SGD, and then we just replace the learning rate epsilon by an explicit regularization coefficient lambda. So now, of course, what we expect is that even if we train with very small learning rates, we should be able to achieve strong test performance by tuning the value of this lambda. And that would like confirm that our analysis is capturing this aspect of SGD. So that's exactly what we see in this figure here. So the blue curve shows you the performance when you train on the original training loss. So you set lambda to 0 with a very small learning rate of, I think, 2 to the minus 9. And then this orange curve shows you the performance when you train with the same small learning rate, but on this modified loss with a finite value of lambda. And you can see that by the end of training on the modified loss does indeed get you better performance. So just confirming that this implicit contribution on the right is actually beneficial in practice. So this second experiment is a little bit more subtle, but we'd like to verify that, you know, not only does this implicit regularize improve performance, but also that the optimal value of this explicit coefficient lambda is close to the optimal value of the learning rate on the original loss epsilon. And so if you look just at the blue curve, so for the blue curve, we're training on the original training loss C of omega. So lambda is set to 0. And as we move to the right, we're varying the learning rate. So like regularization strength is synonymous with learning rate. And so you can see that performance peaks for like a particular value of the learning rate of 2 to the minus 6. And then for this orange curve, we instead fix the value of the learning rate to 2 to the minus 9. So that's why for a very weak regularization, the orange curve coincides with the performance at 2 to the minus 9. And now as we move to the right, we're increasing the value of this explicit regularizer lambda. And you can see you get a very similar peak in performance as lambda increases. And like the optimal value of lambda actually coincides with the optimal value of the learning rate. So that's kind of like further evidence that we're kind of capturing the behavior pretty well. And then in like the final of these simple experiments, we'd like to confirm this analysis is like properly capturing the behavior at different batch sizes. So remember, like one of our claims was that the strength of this regularization is governed by the ratio of the learning rate to the batch size, which many people have also predicted before. So the plot on the left, we're training on the original loss, so lambda is 0, at a range of batch sizes B. And you can see that the performance you achieve on the test set is essentially independent of the batch size, and is just set by the ratio of the learning rate to the batch size, exactly as we predicted. And this is true so long as the batch size is not too big. So this is like consistent with what was expected. And just to provide even stronger evidence, on the right-hand side, we instead train with like a fixed small learning rate, and we vary the value of this explicit regularization coefficient lambda, and we see exactly the same thing. So the performance doesn't really depend on the batch size, but it does depend on the ratio of this explicit coefficient lambda to the batch size B. So, you know, it's kind of promising evidence that we're also capturing the effect of batch size well. Okay, so that was kind of the key experiments, but So one common question that we get when we present this work is, like whether the benefit arising from using finite learning rates in SGD is really a consequence of using finite learning rates, or if it's actually just arriving from the stochasticity in the training process. So what do I mean by that? So you could imagine two processes. So the first process, which corresponds exactly with SGD, we would take steps with finite learning rate epsilon on a sequence of mini batches. So that's what this blue curve represents. But you could imagine a second procedure where we instead sample a mini batch at time t, and then we follow gradient flow on that mini batch for a finite amount of time, epsilon. And then after epsilon time, we draw a new mini batch, but then follow gradient flow on that mini batch, and so on. So in this purple process, we're preserving this kind of stochasticity, but we're eliminating all of the discretization error. And so you could ask, okay, does this purple process still preserve the benefits of SGD or not? So just to answer this question, we just propose this very simple modification to SGD, n step SGD, where we're just going to perform n Euler updates on the same mini batch with a bare learning rate alpha. And then after performing n updates, we draw a new mini batch and repeat step 1. And then we do that again and again and again. So of course, the key trick here is that we've introduced an effective learning rate, the distance traveled when using a particular mini batch, epsilon, which is just n alpha. And so this bare learning rate alpha is defining the discretization error, how large a step you take. And then this effective learning rate epsilon sets this stochasticity. And so we can preserve this stochasticity, but eliminate the discretization error in the limit that this number of steps n goes to infinity. So that's the experiment that I'm showing here on the left. And the thing that's pretty neat to see is that for a range of sort of numbers of repeats n, the test accuracy actually kind of consistently depends on the bare learning rate alpha. But then as you increase the bare learning rate alpha, large values of n go unstable. And so as a consequence, the smallest value of n achieves the highest test accuracy. So essentially, we're kind of confirming here that it is the discretization error that's driving the benefit of SGD. It's not the fact that you're kind of effectively on a time varying loss. And actually, this sort of property of training on a time varying loss seems to be detrimental. It's only the discretization error that's helping. And so this plot on the left, we were training for a fixed number of epochs, meaning that larger values of n were also taking more steps. So you might worry that that's going to bias the results. So you can run the same experiment where instead of fixing the number of training epochs, we just fix the number of parameter updates, and you see exactly the same phenomenon. And actually, if you sweep across compute budgets, that you consistently see that n equals 1 is always the best setting. So to conclude, we've shown that for small but finite learning rates, random shuffling SGD stays close to the path of gradient flow, but on a modified loss. And this modified loss contains an implicit regularizer, which we confirmed empirically does enhance the test accuracy on real world data. And this implicit regularization benefit is arising from the fact that we're training with finite learning rates, and that introduces a discretization error, which turns out to be beneficial. So that's everything. So thank you very much, and I'm very happy to take any more questions.